5 fantastic Fibonacci facts. You probably know already the Fibonacci numbers 1, 1, 2, 3, 5, 8, 13, and so on, where you add two numbers to get the next one. You might have met it in the way that Fibonacci, an Italian mathematician of the Middle Ages, did by looking at patterns in nature. I've tried to draw over here on the right a rabbit. Fibonacci looked at the reproduction patterns of rabbits, and what he found was that the numbers expanded, at least in theory, following his Fibonacci numbers. Also, lots of patterns in nature follow these numbers. I've drawn down here a three-leaf clover. It's very common to find clovers with 3 leaves, 3 of a Fibonacci number, but 4 leaves is very rare and thought to be lucky. Quite often, the numbers of seeds or leaves or other patterns in nature follows Fibonacci numbers. So I'm going to share 5 Fibonacci facts today. The Fibonacci numbers are not only interesting because they appear in nature, but they link also in a fruitful way with lots of other areas of maths. So how are they defined? You add two numbers to get the next one. So if we call the Fibonacci numbers the fibs, f1, f2, f3 and so on, f1 plus f2 gives f3, f2 plus f3 gives f4, and in general, fn add fn minus 1 equals fn plus 2. So the first thing is, we're going to add up terms to form a summation. So the first term is 1. The first term plus the second one, 1 plus 1 makes 2. The first 3 terms, 1 plus 1 plus 2 gives 4. The next terms, 1 plus 1 plus 2 plus 3 gives 7. We're forming a new series, 1, 2, 4, 7. And if you notice, these numbers that we are forming, these summations, are 1 less than Fibonacci numbers. 1 is 2 take 1, f3 take 1. 2 is 3 take 1, which is f4 take 1. 4 is 5 take 1, which is f5 take 1. 7 is 8 take 1, which is f6 take 1. So in general, if you add up the first n Fibonacci numbers, you get fn plus 2 take 1. Or, for those of you who like sigma, that's the capital sigma meaning summation, the sum of fi from I is 1 to n will be fn plus 2 take 1. This result is easily stated and easily checked, but can you prove it? It might be harder than you think. So, divisibility. Look at the Fibonacci numbers. Look at two that are together, any two that are together, consecutive numbers, and ask, what is their highest common factor? Do any of them have a common factor apart from 1? And no matter how far you go, you will never find two consecutive, next to, Fibonacci numbers with any common factor apart from 1 itself. Why is that? Well, if you think about it, take two numbers. If they've got a common factor, let's call it p, that will also be the factor of the next Fibonacci number, because when you add two numbers, if p goes into both of them, it will go into the third one as well when you add them, and it will go into the previous one. So, let's suppose p divides into fn and fn plus 1. It will also then divide into fn plus 2. Because if a number like 7 divides fn and fn plus 1, it will divide the summation. It will also, with the Fibonacci numbers, divide the one that goes before them. So in other words, p will divide the number that comes before fn and fn plus 1. So we'll divide the one before that, and the one before that, and all the way back to f1 and f2. And we know for f1 and f2, there's only one number that divides those, and it's 1. So 1 is the only number that can be the common factor of two adjacent or consecutive Fibonacci numbers. Okay, link with square numbers. f1 times f3, 1 times 2 is 2. f2 times f4, 1 times 3 is 3. f3 times f5, that's 2 5s is 10. f4 times x6 is 3 8s rather, which is 24. Let's now think of the numbers I've left out and square them. f2, that's 1 squared, which is 1. f3 squared is 4. f4 squared is 9, and f5 squared is 25. Compare the two columns, you'll find that f2 squared is f1 f3 take 1. f3 squared is f2 f4 plus 1. f4 squared, 9, is f3 f5 take 1, and this pattern continues. So in general, a Fibonacci number squared, fn squared, is fn minus 1 times fn plus 1 plus minus 1 to the n plus 1. That means if n is even, you take 1. If n is odd, you plus 1. Okay. Fourth fun fact. Pascal's triangle. Remember Pascal's triangle? It's linked with binomial expansions and also combinations. If you remember with Pascal's triangle, we add two terms to get the one underneath. So, if I go with the fourth line, 1, 4, 6, 4, 1, 1 plus 4 gives the 5, 4 plus 6 gives 10, 6 plus 4 gives 10, and 1 plus 4 gives 5. Adding two numbers reminds us of Fibonacci, so what's the link with the Fibonacci numbers? If I write out Pascal's triangle in this way and take the sum of the diagonals, the Fibonacci numbers drop out. So 1 plus 3 plus 1 gives 5, 1 plus 4 plus 3 gives 8, and so on. The Fibonacci numbers emerge from the diagonals. My fifth famous fact is going to be about the ratio of the terms. So we take two terms and divide the larger by the smaller. So starting, 1 divided by 1 gives 1. 2 divided by 1 gives 2. 3 over 2 gives 1.5. 5 over 3 gives 1 2/3. 8 over 5 gives 1.6. Then we have 13 over 8. These numbers are getting closer and closer to a limit, a value they're converging to. And if you continue this with your calculator or a spreadsheet, you'll find the ratio very quickly converges to a number which is roughly 1.618. You might recognize that number as the famous golden ratio, which exactly is called by the Greek letter phi, is root 5 plus 1 over 2. Why is this? Well, we know that fn add fn plus 1 equals fn plus 2. That's the definition of the Fibonacci numbers. So divide through by fn, I get fn over fn plus 1, add 1, equals fn plus 2 over fn plus 1. Now when n increases, this converges, so fn plus 2 over fn plus 1 is the limit, which I'm calling x. But also, fn over fn plus 1 will be 1 over the limit, so 1 over x. So I get the equation 1 over x add 1 equals x. We solve that equation. Multiply through by x and take everything to the same side. I get the quadratic equation x squared take x take 1 equals 0. If you remember the quadratic formula, x will be 1 plus or minus the square root of 1 plus 4 over 5, 2 solutions, and the positive one is 1 plus root 5 over 2, which is the golden ratio. Bonus here, you might have wondered, is there a formula that will take us straight to Fn instead of having to go through every term? So if I wanted F100, is there some formula that will get me there instead of having to calculate F1, F2, F3, and all the way through to F100? There is. This is a bonus. It's called Binet's formula, and it involves the golden ratio. So Fn will be phi to the n take minus phi to the minus n over root 5, which can be written as root 5 plus 1 to the n take root 5 minus 1 to the n over 2 to the n times root 5. Try a value in this like n is 5 and you'll find it gives you the fifth Fibonacci number. Can you use this to find F10 or F100? Yes, you can. In fact, the second term, root 5 plus 1 to the n, quickly goes towards 0. So one thing you can do is root 5 plus 1 to the n over 2 to the n times root 5 and go for the nearest whole number, and that works too. So there are 5 fabulous facts about Fibonacci numbers, and there are many others as well. This is really a series of numbers that pops up in all sorts of places in mathematics. I'm David Forster. This is Gold Standard Maths. Tune in next time for more treasures of mathematics.